This is video clip 2 for topic 3, correlation, EACS 6023, University of Oklahoma. And the last clip we had discussed the concept of correlation and then kind of looked at it in terms of the graphical representation of correlation. With this clip, we want to start to move into the actual statistical calculations involved in correlation. And again, correlation is some type of measure in which you're looking at the relationship between primarily two variables. For the most part, correlations are bivariate, although again there are opportunities to look at more than two variables at a time. Looking at page 8 of your PowerPoint presentation, a couple of statistical terms, a couple of statistical calculations that are very important. Covariance is a statistical calculation that depicts the relationship among variables in unstandardized raw terms. So the difference between the covariance and the correlation, they both do the same thing. In a covariance calculation in a bivariate situation with two variables, if the covariance is direct, if it's positive, the correlation should also be positive. Conversely, if the covariance is negative, the correlation should also be negative. The difference between the two is that the correlation calculation, and there are several different correlation calculations available in terms of mathematical formula, but the correlation is actually standardized, the covariance is not. But again, if one is direct, the other one should be direct as well, because the covariance is actually used in the calculation of all correlation coefficients. That's on page 8. Then moving on to page 9, the most common correlation coefficient calculation that you'll encounter is the Pearson's coefficient. And again, it's a measure of association. The Pearson is denoted typically by in a sample. It's denoted by the small English letter R. And then sometimes you'll see the postscript notations involved. If you are correlating X data with Y data, you could put X, Y. Obviously that's arbitrary though. If I might say that I'm correlating post-test scores for a treatment group and a control group, and I might just call them T and C for treatment and control, or I might call it E and C for experimental or control. So obviously the notation is arbitrary, but it has to be consistent with what you're using to depict your data. But the R is standard. So in a sample, it's a small r. In the population, it's denoted by the Greek letter rho. And we'll talk more about this in the next couple of sessions, but statistically, in terms of quantitative analysis, the primary goal is to take a sample and then use that sample, the analysis of that sample, then to infer out to a larger population. So it's going to become important that we are able to denote the difference between a sample statistic, which we calculate, which represents or estimates a population parameter or a population characteristic in our larger population. So again, if you see the rho indicated somewhere, like for instance in a hypothesis, the rho just indicates correlation, but it's population correlation. Okay, so the Pearson's, just like any correlation coefficient, is a statistic indicating both the strength and the direction of the relationship between the two variables. And correlation coefficients are standardized coefficients, the Pearson and any other for that matter. And they're standardized so that the strongest correlations are negative 1.0 and also positive 1.0. So a perfect inverse relationship would be denoted by a negative 1.0. A perfect direct relationship would be denoted by 1.0. And all other correlation coefficients then fall in between these two. No relationship at all would be denoted by 0.00. So then it's simply a fraction. Any correlation that you calculate is going to be a fraction somewhere between negative 1 and positive 1. It might be 0.38, in which it's 38% of a perfect positive correlation or a perfect direct relationship. So moving over to page 10 of the PowerPoint presentation, a positive R sub xy, or a positive correlation coefficient, is indicative of a direct relationship, and an increase in the x variable is associated with an increase in the y variable. Obviously there are going to be data points that do not conform to that. Now, when you're talking about statistical analysis of data or quantitative analysis of data, it's important to understand you're talking about general issues within distributions of data. There are going to be data points that don't conform to this. You're going to have some instances in which subjects who score high on X might score low on X, even though there's a direct relationship in the overall distribution of data. It's important to understand that distinction. We're looking with quantitative analysis. The idea is to do more of an extensive analysis, give more of a wide sweep, understanding that there are going to be some non-conforming data. Sometimes data are so non-conforming that we start thinking about outliers, and we'll talk about outliers as the semester goes along as well, and what to do when one is confronted by outliers in data. But generally speaking, as subjects increase in X, they also increase in Y if there is a direct relationship and if there's a positive correlation coefficient. And of course 1.0 is indicative of a perfect direct relationship. So how big is big? Well, and how strong is strong? It's all relative. 1.0 is a stronger relationship than 0.5, which is a stronger relationship than 0.3, which is stronger than 0.00. So it's rather relative. Now, when we get to hypothesis testing, we can actually test relationships for statistical significance in the population given our sample. And we'll talk about that again later on as the semester goes along. But inherently, correlation is more of a relative term than anything. So moving on to page 11, obviously the converse of the positive R sub xy is a negative correlation coefficient. And a negative correlation coefficient is indicative of an inverse relationship. And an inverse relationship simply implies that as the data increase on the X variable, they tend to decrease on the Y variable. So, for example, as the number of hours of television increases, if it's non-educational television, one might hypothesize that the attention span decreases, and therefore you might get a negative correlation coefficient between those two variables. And actually on your slide, on page 11, a negative 1.0 is indicative of a perfect inverse relationship. So negative 1.0 is equivalent to positive 1.0 in terms of strength. It's just that in one case it's an inverse relationship, perfect. In the other case it's a direct relationship, perfect. And a negative 0.5 means that the relationship is just as strong, equivalently strong as a positive 0.5. It's just one is direct, one is inverse. So the strength of the relationship is denoted by the absolute value in effect of the correlation coefficient. So it's important to remember that. You might have strongly correlated data, but they're inverse. So don't think that the numeral value is what implies the strength of the relationship is the absolute value. And of course, just to kind of bring that home on page 12, if there's a relationship, if there's a R sub xy of 0, that just means there's no relationship at all. Knowing X data really gives you no extra information about the Y data. If you have a strong correlation coefficient, that means you know something about the Y data given your knowledge of the X data. And that'll be important for some of the statistical analysis that we'll talk about later in the semester. That's one interesting thing about some of these basic statistics is that some of the other inferential analyses will actually use the basic analysis as part of their processes. For example, we get the dependent samples t-test. The dependent samples t-test relies heavily on correlation as part of the statistical calculation of the t-statistic. So again, it's kind of a fundamental statistic. Correlation is a fundamental statistic, not only as a descriptive tool, but also it's used in more sophisticated types of analysis as well. So in the next clip, we'll resume on the next PowerPoint slide.